The main goal of this experiment was to examine the relationship between velocity of an object falling through a fluid and the resistive forces from the fluid. We set up an experiment that helped to demonstrate terminal velocity for an object in the fluid by showing that when an object reaches terminal velocity in the fluid, the gravitational force equals both the viscous and drag force. Using Reynolds number to compare between the fluid types and determine the drag coefficient of each fluid helped to verify the differences between fluids used and the difference in terminal velocity seen. So we hypothesized that among different fluids used, different terminal velocities can indicate different Reynolds numbers, which changes the drag coefficient for the object used. Group predictions closely matched tracker results in showcasing that given 3 different tested fluids, an object falling through will have a different point at which it reaches terminal velocity and will result in a different drag coefficient from the Reynolds number, supporting that there are differences in resistances for objects in different fluids.
The models we included was a free body diagram, which shows the forces pushing up and down on the sphere, and a system schema, which shows gravitational and contact forces between all the objects in the system. The concept that we based our experiment for viscous force on was Newton's second law, and for drag force was Newton's third law. The equations shown are Reynolds number, which is the ratio of drag force over viscous force, and the viscosity equation and the drag equation. The relationship between the velocity of a falling object and the resistive forces from the liquid that is falling through is tested. The same ball bearing that weighed 8.4 grams with a radius of 5.6 millimeters was dropped through 3 different liquids: corn syrup, dish soap, and water, each at 50 milliliters of fluid. Each experiment helped illustrate that an object dropped through a liquid experiences both drag and viscous forces when it reaches terminal velocity. However, the Reynolds number helped to indicate whether a drag of viscous force is greater, because drag force is of less importance than viscous force due to a small Reynolds number. However, the purpose of using 3 different liquids was to target whether or not the ball bearing could actually reach terminal velocity by finding the negative slope, the derivative of the position graph, and thus have a 0 acceleration on tracker. Given this terminal velocity value, we then can find Reynolds number in each of the coefficients of drag, the resistance of the ball in the fluid traveled in. However, one experimental flaw that happened in the water trial was the lack of distance provided as the ball traveled in the fluid, preventing the ball to be able to reach terminal velocity. Therefore, if we were to do this again, we would lengthen the distance that the ball has to travel in water, and inconsistent clicks to track the ball, too far ahead or too far behind on tracker, led to a slight bit of scattered velocity and acceleration graphs as another example of experimental flaw, but showed a relatively readable graph. Some of these flaws led to a result inconsistent with our model when comparing the coefficient values for each fluid used and how it relates to terminal velocity for each fluid.
When a ball is dropped in a fluid, it experiences both drag and viscous forces opposite of gravitational force, and when the ball has reached its terminal velocity, there would be an indication that these forces have become equal from a constant velocity graph. So the point at which the ball reached terminal velocity differed between the fluid type used, which differed the Reynolds number value because drag coefficients are specific for the shape of the object in the fluid and are correspondent to the Reynolds number used. So a change in Reynolds number would indicate different measured coefficients or resistive forces for the object in the fluid. So because we know the coefficient of viscosity of the fluid used from online sources and not the drag coefficient, which corresponds to the Reynolds number produced, drag coefficients in the fluids change depending on the Reynolds number found due to the difference in terminal velocity measured. For example, corn syrup data show that it was able to reach terminal velocity immediately, where its terminal velocity was negative 0.17 meters per second. The top graph from tracker showed position, which was linear, and the derivative position graph is a terminal velocity, since velocity graph shows constant position for velocity. So on the velocity graph in the middle graph, velocity is relatively constant other than the clicking flaws that occurred. Acceleration is at the bottom of the graph. But again, we recognize that there should not be an acceleration, which is why the acceleration graph is flat.
Thus, given Vt, the measured coefficient of drag force for corn syrup was 19.48 because there was a change in the Reynolds number, and so the standard coefficient for drag was changed. The calculations show how the coefficient for drag force can be found using the terminal velocity, considering that the standard drag coefficient for a sphere was not used, since this value is specified for a specific Reynolds number. Changing the Reynolds number can exhibit different resistive forces on objects in different fluids. The dish soap data showed it was also able to reach terminal velocity from the velocity graph leveling out and being constant. The terminal velocity was negative 1.49 meters per second. The acceleration was also quite leveled at 0. The coefficient for drag was 0.287. For water, the data did not appear to have reached terminal velocity according to the velocity graph, whereas not at a constant velocity, so this trial would still have an acceleration.
Overall, the higher the density of the fluid, the lower the terminal velocity of the sphere due to opposing forces. Furthermore, the resistive force investigated is different from macroscopic friction because kinetic friction reduces the speed at which the surfaces slide across each other, so no kinetic friction means the object would continue to slide in the fluid. Reynolds number explains that the fluid with higher drag force over small viscous force will cause the object to move at a slower terminal velocity due to the forces pushing up on the object and opposing the gravitational force that pulls it down. So corn syrup had a higher viscous and drag force than soap, that the sphere will drop at a lower terminal velocity. Since dish soap had a higher drag and viscous forces than water, the sphere will drop at a slower terminal velocity than just plain water.